and not a rollup because they don't settle the data availability layer is not Ethereum. They have a data availability committee. Also, StarkX is permissioned, right? Just not like anyone can go and deploy whatever they want. Companies like DYDX, they actually talk to Starkware, hey, we actually want to have futures and perpetuals. And Starkware created the system for them and just giving an API to interact with the system. And under the hood, it creates all the CK proof and all the security of the system. But then the second iteration was to actually create a Starknet, right? So it's using all the learnings from StarkX, the same programming language, Cairo, but now let's make it an actual layer 2 rollup that is permissionless, so anyone can create a smart contract, anyone can deploy. And that is what I'm actually going to talk today. And the Starknet Foundation is a fairly recent organization. I think it has like a 1 year only, which the goal is to push for the decentralization and the evolution of a Starknet. And it's a very common pattern as you see as different layer twos. It starts with a company who pioneers the technology and then moves towards a foundation for a more credible neutrality. Okay, so now that out of the way, the topics that I want to cover today is a little brief summary of why we chose to use Cairo, which is our own programming language that is not Solidity, obviously. Then why we actually created Starknet, why it exists. And then we talk about a very important feature for me in layer twos and in Starknet is the idea of a smart wallet, which is connected to the account abstraction. I'm going to do some live coding, so I show you guys how a very simple smart contract with written in Cairo will look like, and hopefully have enough time to deploy to testnet. And then next steps for where you can continue your journey if you want to learn more. So yeah, first of all, so why Cairo? So I like to explain this with an example. Like, imagine that you're the head of a small country and you're in charge of the space exploration agency, and you're supposed to launch a spacecraft to Mars, right? So to do that, you need to know some variables. For example, what is the best launch window? What is the best trajectory to get there? And those are very difficult to calculate variables, and you have to get it right in order to be successful. So most likely you will task your engineering team, say, hey, could you create a program or an algorithm that will calculate those two variables for me, and then we'll know when to launch the spacecraft in a way that we use the least amount of fuel, right? So probably the team will use language like Rust, for example, something very high performance, or C++ to create the program. But then they have a problem, right? This computation is very taxing, requires a lot of resources, and it requires actually a supercomputer that they don't have. It's a small space agency, a small country. So the only chance they have is to actually collaborate with a rival country that actually has the resources, the supercomputer, to execute it for them and to give them the answer. So that country agrees to participate. So the way that will work is that you give them your program, right? They will run it in the supercomputer, and sometime later they will tell you the results, right? This is the trajectory, this is the launch window, which is all good, but then you have some question, right? This is a rival country. How do you know that, first of all, the supercomputer didn't malfunction while executing the program? Or even worse, what if a rival spy agency tamper with the execution, even just a little bit? So the result is a little bit off, but it completely just enough to derail the whole space program. You just don't know. You just know the result. The only way for you to have certainty will be to get another supercomputer to re-execute the program and compare results, but you don't have those resources. Uh, so with a language like Rust, like C++, you don't have that guarantee. You don't know. The only way to know is to re-execute and compare. Now, if you had done the program with Cairo instead of something like Rust, you will do the same pattern. You will give them the program. They will execute it using the Cairo VM. But now when they get back to you, not only they give you the result, they give you a validity proof that attests to the integrity of the execution of the program. And you can take this validity proof and you can verify it in a laptop or even a smartphone. And if it passes the verification, you have almost 100% certainty that the calculation is correct. That if the execution is intentionally or unintentionally modified, the proof will be invalid, and you will notice right away. So this technology, what in essence allows you is to have a supercomputer where a regular computer is able to keep a supercomputer honest, right? if anything happens, someone trying to tamper, even if the hardware malfunction, you will detect that the validity proof will be invalid. So that's the superpower of Cairo. So some of the features, the first one that I mentioned is that Cairo allows to create a new type of program that's called a provable program that you can prove the execution. Now, it needs to run on top of its own virtual machine. It's called the Cairo VM. This is why we're not EVM compatible, right? We don't use the Ethereum virtual machine. The syntax of Cairo, at least of the modern version of the language, is heavily inspired by Rust. So if you know Rust, you will feel right at home with Cairo. It has a very similar ownership model. If you know about Rust, how it works, it's similar in that regard. It's a strongly typed. It uses traits and macros. So you will see there's no inheritance, like in the case of Solidity. So it's based on traits. And for me, very interesting enough is that you can use Cairo on its own. You can use it also to write smart contracts for a Starknet, but you can also use it for any generic program that you have in mind. And the best of all is that it takes advantage of validity proof to create this attestation of the execution, but in a way that is completely transparent to you as a developer. You don't need to know anything about ZK to take advantage of these properties. So it's a very good job at abstracting away those complexities. That before, for example, with Circom, it was not the case, right? You need to have some idea what's happening under the hood. Now, just to give you a taste how the language looks like, this is how you define a custom data type with a struct, very similar to Rust. This is how you define functionality that you can share among different types, in this case, a trait. This is how you actually implement that trait, which is now the syntax is a little bit different from Rust, right? So you can see that it's heavily inspired, but it's not exactly the same, the syntax at least. So to summarize, why Cairo? First of all, it creates it allows the creation of provable programs that give you a proof of the computational integrity, right? That nothing failed, no one tampered with the execution. That you're able to verify its integrity without having to re-execute the program to know that it's actually the right result. It's a very powerful and flexible language because it inherits a lot of the properties from Rust. And it prevents cheating and also malfunction as well. So it's able to keep a supercomputer honest. So before I move on, any question about Cairo itself?
I have a quick question. So
Yeah.
what's the advantage between Cairo and those fully EVM compatible ZK technology?
The ZK EVM,
Yeah.
the way I like to think of it is that, Solidity, right, is custom made for smart contracts. Did you ever try to create something that is not a smart contract with Solidity, like a general purpose programming language? No, it's not really possible, right? It's custom made for that purpose. I like to think of Cairo as the way that Python is to Django, right? So you can use Cairo for any type of programming language, but if you want, you can use it to create a smart contract. The same way that in Django, you can use Python just to build, a REST interface or whatever you want. So it gives you way more flexibility, and it opens the door to different use cases that wouldn't be possible with a CK EVM. Also, when you look at under the hood about how CK EVM works to create the validity proof, think about the EVM was never designed to be used with CK technology, right? It was meant to use with a regular traditional computer architecture.
Mhm.
So they have to do a lot of transformation under the hood to make it compatible with CK circuits, which is fairly inefficient when it comes to proving, right? So as time goes by, we try to optimize for the long term. Like, what is the most efficient technology for proving? Because proving is going to become a bottleneck at some point with all these CK layer 2 technologies.
So,
So our bet that Cairo is going to be way more efficient in proving that
so
CK EVMs.
do you have any numeric comparison between proof generation between Cairo and those ZK EVM?
Oh, you mean like benchmarks?
Yeah.
No, that I'm not aware of benchmarks yet,
Okay.
because a lot of these proving systems are not yet, let's say, are so new, and not many, maybe not all of them are open source yet, so it's hard to do. But eventually, they're going to come out. It will be interesting to see.
Okay. Makes sense.
I also have another question. In regards to the proofs, are you able to give a little bit more detail there? Are you able to prove any arbitrary program that you're writing? Because naively, it kind of sounds like a solution also to the halting problem if you can kind of prove anything. But that's of course impossible. So I'd like to understand a little bit better what the proofs do.
You can prove any program, like anything that you can create with Cairo as a programming language, you can prove it. I mean, there are some limitations, right? Like for example, the Cairo VM is very good at certain things, but it's very slow for example, if you want to create a hash, let's say a SHA-256 hash, actually it will be very inefficient to do that, right? If you want to use the elliptic curve that Ethereum uses for sending transactions, it's not very efficient for that. So the way that it evolves to solve these issues is that the CPU, it starts to have its what's called built-ins. It's like a custom-made circuits just for specific purposes, like Ethereum elliptic curve or hashing. So yeah, some edge cases will be hard to do efficiently with a language like Cairo, but for the most part, you can use Cairo for any type of programming language, and it's actually being used very successfully for gaming as well.
Mm-hmm. Okay, thanks.
Okay, right. Let me continue. All right, so we talked about Cairo. Let me now talk about Starknet, like why we actually came up. I mean, not we as a foundation, but Starkware, why they came up with that solution. So if you think about the problem of a scaling on layer one, is like when you have a block producer on Ethereum, right? They propose a new block. Let's say, oh, the new state of the whole network is 42. Now that's what the block producer says, but the other validators of the node, they just don't take their word for it. What they do is that they take the block and they actually re-execute the transactions in the block and verify that they actually get to the same result, that they actually get 42, the same global state. And that is happening over and over thousands of nodes around the globe doing the exact same calculation, right? So you can see that the system is very robust, it's very inefficient. Even a small calculation actually takes a lot of power of the whole system because it has to be re-executed every single time in all the machines. Now, in the case of a Starknet, which is the same as any other ZK layer 2, when you propose a new state, you also get the validity proof, right, to Ethereum. So now the Ethereum validators, they don't have to re-execute the whole transaction to have certainty that the output is actually 42. They only have to verify the validity proof. And the effort to do the validation is only a fraction of the effort of actually doing the computation. So this is where you gain a lot in performance. You can see that now the effort of creating the block is a little bit bigger because not only you have to do the computation to see what is the new state, you also have to create the validity proof, which takes more resources. But the benefit is that you pay that price only once, right? And you do it off-chain, which is cheaper. So the idea is that you execute only once, but you verify everywhere because verification is very cheap. Now the question is how cheap it is. So if you assume that the program that the sequencer is running takes X number of steps to do a computation, so the verification of the validity proof associated with that will be log square of X. This is log base 2. So it's polylogarithmic. And an easier way to see this in a chart, right? So the blue line will be the effort of the sequencer, and the yellow line is the effort to verify that validity proof on layer 1. So as you can see, like the more complex the computation is, this gap becomes wider, and that's what you gain in performance. This is a type of compression of computation. And this is just like the baseline of the system. It actually gets improved a lot with recursion. You know, now that I'm here, let me just share this slide with you so you can follow along as well. I forgot to do that at the beginning. Let me do it now. Just polish it. Because I have links here to Wolfram Alpha, so you can check the math yourself there. Okay, I'm gonna put it here in the chat.
What are the axes on this graph here? Is it number of transaction and time, or what is it?
It's the y-axis will be the number of steps, which is like the number of CPU cycles, and the number of CPU cycles for the time. Let's see. That's why I put the link here to
This
Wolfram
should be like
Alpha.
a circuit size, right, or something, the x-axis, because your logarithm is with respect to, you know, the runtime of the computation.
Yeah.
Which
So the
translates to
x is the number of steps of the computation, and then the y is the number of steps depending on the system, right? For the case of the sequencer, it's linear. In the case of the verifier, it's polylogarithmic. Good questions. Any more questions?
So what is the overhead of generating this proof? I understand that it's only done once, but still, out of curiosity.
Yeah, so the proof generation will be x log x.
X log x.
Yes. But that's only the base case. With proof recursion, that all things get improved a lot. So I only have 1 hour today, but I want to give you the resources at the end where you can go to find out more about that information.
Okay.
This is for the verification only, because this is the effort that is done on Ethereum, which is the expensive part, right? We have to pay for the transactions and the block space on Ethereum for that. The proving happens off chain, so it's cheaper in that regard. But the prover machines are beefy machines. It takes a lot of effort to create the proof. That's what I'm saying. At some point, it's going to be critical that the efficiency of proof creation to be high.
So is it fair to say that for the proposer, the complexity is going to be x plus x log x?
No, because the x log x is the combination of the execution and the proving.
Oh, sure. Okay, sure. Yeah.
Okay. So I like to think about validity proof as a way of compression, right? The same way that you compress a file with zip, you compress a computation with a validity proof. And that's how we manage to actually scale on top of Ethereum without sacrificing security, which is the important part. So a validity proof is a use case of zero knowledge proofs. And what it does is convinces a verifier on layer 1 on Ethereum that a new layer 2 state is correct without sharing the transaction details. Like, you don't need to re-execute, so you don't need the details of the transactions to have certainty of the output. This doesn't make the layer 2 transactions to be private, because at the end, Starknet is an open system, it's an open ledger. You can just connect the dots if you want. It just makes the verification very efficient, what they call it succinct. So we prefer to talk about Starknet to being a validity rollup because it's based on validity proof instead of a ZK rollup, just because ZK has the implication that it's something about privacy, which is not the case of a Starknet, right? Starknet is open. And the system is based on ZK Starks, not ZK Snarks. You have probably heard about Snarks in the past from Ethereum. This is a slightly different technology. And what it gives you is very efficient proving and verification. So I have a very high level comparison between Starks and Snarks. This is a high level because there are little nuances depending on which particular protocol you're using. But the verification of a Stark is polylogarithmic, right? The line that I show you. In the case of a Snark, it's actually constant. It doesn't depend on the complexity of the underlying computation. The size of the validity proof, the thing that we send to layer 1, in the case of a Stark, is actually 400 kilobytes. In the case of a Snark, it's a couple of bytes only. Now, you'll think, okay, it seems like a Snark seems to be much better than Stark, so why did we bother? And the answer is this, right? Proving with the Starks is an order of magnitude more efficient than the Snarks. You don't require a trusted setup for the system, which you do with the Snarks, right? In the Snark, you have to somehow have a secret that is shared between the prover and the verifier. And if that secret gets leaked, the system gets compromised. That is not the case with the Stark. So it's a higher security guarantee. And also, the Starks are deemed to be quantum secure because the only cryptographic primitive that is relied upon is the hash function. The rest are just polynomials. The case of the Snarks, they're not quantum secure. So whenever the first quantum computer with sufficient power comes online, they won't be able to break Starks, but they might be able to break Snarks. You have any questions about here? The slide seems to usually draw questions.
Is there any more into the trade-off space between the Starks and Snarks?
Is there more information that you can get from that?
Yeah, like
in any particular area?
Because really from this data, it makes really more sense to just use Starks altogether. But I remember that there's I remember like a year ago, I don't remember the exact details, but there's like a broader trade-off space
Yeah.
that could benefit depending on either Snark or Stark. So I was wondering if you know that off the top of your head.
No, not aware. Also, I'm not a cryptographer, so I cannot go that deep into the differences. I just know that, for example, Ethereum seems to favor snarks just because they're able to do the ceremony, right, very securely to create this secret, and they're going to be very good at that. So if they do it properly, yeah, it's very cheap to share these proofs within the system. But the question is every other system relying on snarks are going to be so so good at creating this secret and protect it and not let it be leaked? That's the question. You have to make sure that they actually do it correctly. So yeah, I can at the end I'm linking actually some resources on how Starks work, the math behind it. So maybe you can want to take a look at that to know how this is achieved. Now, a common question that I get is like, why did we choose to have our own virtual machine and not be a CK EVM? I actually touched on that before, but at a high level is that because we have a long-term vision of the system, right? And we really care about performance. And we're sacrificing compatibility, right? Because right now, you cannot just deploy a Solidity smart contract to Starknet, right? It wouldn't work. But by having a system that is custom-made from the ground up for this new paradigm of ZK proofs, allows to maximize to the point that we will have the best performance of them all. But of course, we have to bootstrap a whole ecosystem based on Cairo and tooling on top of that, which is not easy to do. If you read Vitalik's blog post a while ago, that he had a classification of ZK EVMs type 1, 2, 3, and 4. This is where things stands right now. So type 1 will be a CK EVM where you can deploy pretty much any Solidity smart contract directly to this CK EVM and it would work. The downside is it will be very slow, right? Because the EVM was never meant to be used in the CK secret. So things that are easy to do for a traditional CPU architecture are very hard to do for a ZK circuit. Now you have the type 2 CK EVM, which for the most part is highly compatible, but there might be some changes on how storage and the storage data structure is defined. So it's still slow. And basically, there are no projects that I'm aware of that are type 1 or type 2 right now. Now in type 3, we actually have projects, right? So the compatibility with Ethereum or with Solidity will be partial because now certain precompiles will have to be different, certain hashes will need to be different, storage as well. But you have fast performance, right? And this is where you see projects like ZK Zinc, Scroll, Polygon ZK EVM, but you also see Kakarot. And Kakarot is an interesting use case that they actually took the Cairo VM and they're creating a layer 3 on top of Starknet that actually works as a bytecode translator between the EVM and the Cairo VM. So what allows you is that you can deploy Solidity bytecode to this layer 3, and under the hood, it transforms into a Cairo VM bytecode, so you can, use all the tooling for Solidity for Ethereum on top of this layer 3 called Kakarot. Now, the type 4 ZK EVM is the ones that have a completely different virtual machine, as is the case of a Starknet. The benefit is like a very, very fast, but you don't have compatibility. And here you can find Aztec is another one. I put an asterisk because Aztec being privacy focused, they might have different set of trade-offs. But you can also find Polygon Mining, which in some regards, technologically, they have some similarities with Starknet as well. So this is where Starknet sits. And Kakarot, which is a project, an offspring of the Starknet ecosystem, also sits. Talking about finality, on Ethereum right now, it's about 6 minutes, right, to get finality. In the case of an optimistic rollup, it's about a week, right? That's the time that you can actually withdraw asset from layer 2 to layer 1. In the case of a Starknet, it's about 2 hours, the time you have to wait between when you want to withdraw assets from layer 2 to layer 1. But the finality between the layer 2 itself is about 3 seconds only, right? So you get a much better balance with a much higher security guarantees than an optimistic rollup. And finality is pretty fast too.
So why is there a discrepancy between 3 seconds and 2 hours? Like you generate proofs in 3 seconds, but you post every 2 hours, or what?
Right. So 3 seconds, and it's when the transaction gets executed without the proof, just execute it and put it in the block, right? So it's like a soft confirmation, but you don't have at that point the validity proof being created. For
So-
that, you have to
Okay, so
wait
2 hours to generate the proof. Okay.
Right. So it's a different level of security that you're getting. In this case, you kind of have to trust the Starkware because they control the sequencer. In this case, you don't trust anyone. It's just the ZK proof.
So given that the proving time is much faster for Starks versus Snarks, like why? Like, what's the reason for waiting this long? Because I think like the other ZK VMs, they wait about like an hour and a half.
It's configurable. It's about cost, right? It's about how many
Yeah.
transactions can you fit into a single proof in a way you can spread out the cost, right? Initially, that was
Yeah.
8 hours. So the thing is, as we get more traffic on a Starknet, we can put more transactions in the same validity proof, and maybe even make it shorter, right? We don't have to wait that much to have enough transactions to justify the cost. So it's
yeah, so it's mostly
configurable.
the data availability costs of Ethereum then for
The
everyone.
data availability cost is the biggest cost for all the layer twos. It's like 90% of the cost of a layer two transaction is just paying for data availability. So it's not even the verification of the proof. Yeah. This is why I found proof recursion to be so interesting, because this is how you can play with those settings and you can see how it affects the cost and the time to finality as well.
And so how many transactions do you add in a block, or maximum can add in a block? And then what is the prover? Like, just curious on the specs of the machine that's used to generate it.
So I think right now, for a Starknet, the size of a block, I think is something like 8 million steps. It's just Cairo steps, so it's like a CPU cycles in Cairo. I don't know in transaction because we have a kind of abstraction. So a single transaction is actually multiple user operations. So it's not like a apples to apples comparison. But the size of the block is much bigger than Ethereum, that's for sure. So you can do way more complex computation on it. But I cannot tell you exactly how many transactions. I have some stats here that might give you some idea. For example, the highest recorded TPS was 47. But again, this is not taking into account a kind of abstraction, because each one of these transactions actually could be 10 transactions, 20 transactions, right? Or user operations. So there's another stats that we call it the user operations per second. And the peak right now is 238 user operations per second. This is the closest you can find, for example, to Ethereum TPS, the closest comparison. Because in Ethereum right now, I think a kind of abstraction is not yet widely being used at the moment.
What do you mean by user operation?
Right, like imagine you're in a something like Uniswap that you have to approve certain spending of tokens and then actually do the swap. Normally those are two transactions, right? With a kind of abstraction, you can actually combine those two things into a single transaction. But the two things that you do inside, the approving and the swap, they're called user operations. So you reduce a lot of the overhead because now it's a single transaction. You also have the benefit of executing them in sequence. But they count as a single transaction, even though it's two different user operations. Does it make sense?
Yes. Thanks.
For example, you can mint, I don't know, 10 NFTs in a single transactions on a Starknet if you want. So to summarize, why Starknet?
So what
Sorry,
was
yes.
the machine that's used behind the scenes? Like, curious how beefy it has to be.
For what, the sequencer, for the prover? The two machines.
Prover, yeah. Who generates the proof?
The prover, let's see. Sharp is a proving service that not only serves the Starknet, it also serves all the StarkX apps, DYDX, immutable, blah, blah, blah. That machine has multiple provers inside of it. And I think each prover, it uses something like 500 gigabytes of RAM. So they're really powerful machines. And it has, I don't know, tens of those provers inside of it. And even you will think that's beefy, that is one of the most efficient machines you can find. But again, I don't have stats to compare with other systems, so it's hard to tell. But right now, that's where it sits right now for the Starknet.
Do you use GPUs to parallelize?
Not that I'm aware. Well, I don't know. I don't know that much detail inside the prover. No, I don't want to speculate because I don't know. But what I do know is that proving is a type of work that can actually be breaking down into pieces and parallelized very easily. So there's potential there for something like that. But I don't know exactly how it works. All right. So to summarize, why Starknet? First of all, it's optimized for ZK technology. So you get more computer power, paying less for gas fees. It is secured by ZK Starks plus Ethereum because we send that to layer 1. It has a very powerful programming language in Cairo. It is battle tested because we have been using this technology for about 2 years now, and it has helped secure about $1 trillion in transactions if you consider Starknet and StarkX, because Starknet and StarkX, they both share the same proving machine or the same proving service, Sharp. And I have to update this because it used to be 10 hours, the other one, now it's 2 hours. And you don't require any trusted setup for Starks. Let's see how we're doing in time. Okay. Any questions about Starknet before we move on to smart wallets and account abstraction? All right, let me continue. So what is a smart wallet? So it is a wallet that allows you to sign transactions using something like Touch ID or Face ID, and you can execute multiple operations in a single transaction, right? This is what I mentioned before, the UOPS, user operations per second, why it's a different metric compared to what we see in Ethereum. Now, this is possible because it's using account abstraction. So every single wallet on a Starknet is actually built on top of account abstraction. There are no externally owned accounts. And that is a big win because it means you have a lot of flexibility on how wallets can be designed and the kind of use cases that you can provide now, thanks to account abstraction. We have two main providers for wallets right now. One is called Argent and the other is called Bravos. So the screenshot here is from, I believe, Bravos. So when I talk about multiple user operations, and it's actually called the multi-call. So let me explain how it works. Traditionally, or it used to be the case on layer 1 as well, if you have to perform 2 different steps for certain workflow, for example, approving and swapping on an AMM, you will have 2 transactions, right? One for each step. And most people will believe that because you approve them in that sequence, they're actually going to go and fit nicely in a single block in the same order that you define them. But that is not the case, right? Those transactions could be in the same block, but in different order, or they can actually go to different blocks as well. You have no control over that. That depends on the mempool, that depends on the price, all of that, which opens the door for MEV extraction, right? Could be man in the middle or sandwich attack. So you are open to this type of extraction of value. Now, in the case of Starknet, because we have multiple, thanks to account abstraction, now you can actually have multiple user operations in a single transaction. So you can bundle those. So now if you have the same 2-step process, you actually have a single transaction, which guarantees you that they're actually going to go in a single block in the exact same order and nothing in between. So now it actually alleviates a lot of the issues with MEV extraction, and it makes transaction cheaper because you reduce a lot of the overhead of the transaction, right? Each transaction has a lot of overhead for itself, a lot of extra validation, and now it's a single transaction. And you can have 10, 50 user operations in a single transaction. That's possible. I'm talking about account abstraction, but what that is basically the decoupling of the signer from the account, which when you have something like, I don't know, a ledger, the same device has both things. It's both the signer and the holder of the assets. In this case, because they are decoupled, so the signer is the thing that signs transactions and also identifies a user through a private key. Now, the account is a smart contract on a Starknet, is the thing that holds the assets. It verifies the signatures. So you can have some flexibility. How do you want to make that verification? And actually, the entity that executes the transaction using the multi-call pattern. So the way it works in practice is that, for example, your smartphone could be the signer. You might have some wallet UI. So whenever you want to interact with a smart contract on a Starknet, you actually need to have the other part, the account contract is a smart contract deployed that is assigned to you. So when you sign a transaction, sorry, before I go there, that account contract is a Starknet smart contract that has to comply with a specific user interface that is defined by the SNP6, and basically have an execute, a validate, and its valid signature methods there. So now when you want to execute a function on another target smart contract, what you will do is to sign a transaction, you send it to your account contract, the account contract validate the signature, and now on your behalf calls the target smart contract and does the operation that you want to perform. So that in a nutshell is how account abstraction works. Now, things that you can do with account abstraction is flexible signature verification, which means that you can program how do you want to verify the transaction signature. And that opens the doors for things like, for example, you can have a wallet that is a single signer, or maybe the signer is a hardware signer, right? Like your phone has a dedicated hardware for that purpose that you can use. You can have social recovery. You can have session keys, for example, in gaming, so you don't have to sign every single transaction yourself. You delegate that for temporarily and over a maximum amount to a third-party service. Because it's flexible, you can use different elliptic curves to send transactions. You can use the Stark-friendly elliptic curve, which is native of Starknet, but you can also use Ethereum elliptic curve if you want, or you can use the standard elliptic curve from your phone or your laptop to sign transactions. So an example of this that I love to see always is how you can combine that with the secure enclave of your phone. So when you have a kind of abstraction, you can turn your smartphone into a real hardware wallet. And the way it works, because the phone has two systems, right? You have the shared system, we have the shared processor and memory, which is used for the OS and your application that you installed. But then you have the secure enclave, and this might have different names depending on the brand of your device. This is named for Apple. You have a dedicated processor and dedicated memory for things like, for example, the random number generator, crypto keys management, having different private keys, for signing with hardware using this particular elliptic curve, which is the standard elliptic curve, and the thing that controls something like keychain, touch ID, face ID, right? So with a construct, you can actually make use of the secure enclave to sign transaction, which gives you a much higher degree of security than your regular old wallets that used to use the shared system, which is not as secure because it's shared memory and processor. Now, this is called secure enclave with Apple, but different providers have different names. Like Google has Titan M, Samsung has Knox, ARM has Trust Zone. So every device has something similar that now you can take advantage of, because you can use this elliptic curve to sign transactions on a Starknet. Yeah, you have that flexibility. And also applies for laptops as well. So to summarize,
How do you do recovery on these wallets?
So in the case of Bravos, so you will have both. You have the 24 phrases, and you can optionally enable the hardware signer, right? So the hardware signer will be like the override. So the private key that you derive for the 24 the seed phrase, it only allows you to define who is going to be the private key for the hardware signer, nothing else. It cannot sign transaction for moving asset or anything else. To move assets or the rest, you will have to use your smartphone hardware signer. And they have a system for even move from one smartphone to the next if you want to upgrade. I think you can go, if you go to Bravo's website, you can see all the different processes that this enables and how it uses the secure enclave. It's very interesting. But you will have both, right? The seed phrases and now the secure enclave as a private key. It's just what you can do with both of them is different. To summarize, so a smart wallet, it gives you a much better UX than a regular wallet. You have things like multi-call, hardware signer, social recovery, session keys, all these enabled by account abstraction, which applies to every single wallet on a Starknet. And what it does is the coupling of the signer from the account. So the account is a smart contract with a specific interface. It also supports sending transactions with different elliptic curves, right? So you can use different devices. You can even use a ledger to send transactions on a Starknet. And as I mentioned before, in a Starknet, every single wallet is a smart wallet. There are no EOAs. Okay. Any question before I move on to do some live coding? I have 15 minutes, but I would like to show you a little bit of the coding. But any question about smart wallets and account abstraction? question. Anyone has coins on Starknet to bootstrap my wallet? We have a faucet for the testnet if you want to give it a try there. I don't have extra. The Stark token is not even out yet, actually. All right.
Okay.
Yeah. Question.
No, just sad.
All right, let me stop here for a moment and let me jump into, I have a virtual machine here, Ubuntu, so I can start from scratch. All right. So we need to install, first of all, Cairo, the Cairo compiler, enable to create the coding compiler to the Cairo VM bytecode. So that one is called Scarp. Let me show you here. Open the browser, increase the font size, go to Scarp, Starknet. Right. So Scarp is not only includes the compiler, but it's also a package manager for Cairo, which is super cool. And now we have a package manager for something that is smart contract. So we need to install it, and the quick installation is here. So I'm just gonna copy this link and the font size. Paste it. I don't think increase the font size of this. All right, there you go. All right. So let me source. I'll just close the shell and open it again. If it's Scarp. So Scarp now is installed, which means I can create a new project. Scarp new. Let's call. I'm just gonna create a simple counter smart contract. Which basically I forgot to show here that what we're gonna do. The goal is to this. To install. It's loading. Okay. To install the Scarp compiler, create a new project. When I configure it to be used for Starknet, because as I mentioned, you can use Cairo for vanilla projects or for Starknet, so you have to configure to be for Starknet in particular. And then we're going to create a smart contract that is just simple counter with 3 functions: increase counter, decrease, and get counter. And then hopefully, if I have time, deploy it to testnet. All right. So we have the project. I'm going to enter the counter contract. VS Code. And yes, I trust. Let me increase the font size. I'm going to install the Cairo extension. So you get nice syntax highlighting. The Cairo 1, right? The Cairo is the old one. This is the new version of the language. Make sure to install that one. It's installed. So you can see the project has a couple of files. We have the scarp.toml. We have the name of the package, which edition. This is the prelude. And then you can define dependencies. And then you have a sample smart contract, which is simple Cairo code, vanilla Cairo code, not a Starknet smart contract. You can see like a Fibonacci thing. So with a test, I'm going to remove this and do it from scratch. We can create a new smart contract. All right. So to be able to compile for a Starknet, right? Because right now this is for compiling vanilla Cairo. We need to tell him that it's a Starknet. So let me go to the documentation, Starknet. I need to add this line. The target smart contract, the Starknet. I'm gonna put it here. And then I also gonna add a dependency Starknet. It's like a plugin for smart contracts. Oops. Okay, that's the whole setup. Now I can actually start. And a smart contract is actually a module. So I'm gonna collect the counter module. For this module to be recognized as a smart contract, we need to use an attribute, right? This is the idea of the meta programming that is also common in Rust. So I'm going to use the attribute Starknet contract. Oops. Now, because a smart contract, it needs to have internal storage, and the storage is defined with a struct. Storage, again, it's not any struct. It has to be a struct that represents the storage. So we need to use an attribute for that. The attribute is storage. right? So this is the most basic smart contract without, it's just pretty much empty, but that we can actually now build. And right, the space builder, but it's not doing anything right now. So the first step is to actually define the storage variable. And because it's a counter, we just need to define to store the counter variable, right? So I'm going to define it here. And I'm going to find the type to be an unsigned integer of 32 bits. We have unsigned integer of 8, 16, 32, and 64. And you can go to the documentation to see all the available scalar types. Now that we have the counter, I can define the constructor to define the initial value of the counter. So we create a new function called the constructor. Now to tell the compiler that this is not just a function, any function, but a function, the constructor of a smart contract, we use again an attribute called constructor. And the first argument of a constructor will be the state of the smart contract, right? That is passed automatically. So I'm going to pass it as a reference because I'm going to modify it. And that one is called the contract state. So this is how it's passed automatically. And now we can read and write this to the state. But also when we deploy, we need to pass the initial value, right? The initial counter value, maybe the same type, unsigned integer 32. So now I can, let me write that value to the storage so I can say, let's take the self and give me the counter variable and write to it. And here I'll put the initial counter, right? So that's it. We deploy and we store that value in this particular storage variable. Great. Now we need to define the public interface of the smart contract, the get counter, increase and decrease. So we define public interfaces using a trait. I'll put here trait, and let's call it the I counter. And this trait is going to depend on a generic. I'm going to call it T, but that eventually is going to be the state of the smart contract once we implement the trait. And the functions is going to be the get counter. Counter. The get counter, again, as a first parameter, is going to receive the contract state, in this case, as a generic. And because this is not supposed to modify the state, it's only supposed to read, we pass what's called a snapshot, right? This is like I said, the immutable version of the contract state, so we cannot modify it. And we're going to return the counter, right? So it returns use32. We also need to have the increase counter. And increase counter actually modify the state, so it actually requires a reference to the storage or to the state. It doesn't return anything, so that's about it. And then we have the opposite, decrease counter. Basically also modify the state. There you go. This is just a vanilla trait. We need to inform the plugin, hey, this is actually the public interface. I want eventually an ABI to be derived from this. So we need to use an attribute, Starknet interface. Perfect. So now we have to implement the trait, right? Because this is only the blueprint of the ABI. But now, okay, what do we actually do when we call these functions? So I'm going to bring the trait into scope here. Use super I counter. So now I can actually implement it here. I can say, just looking at my example code here, right? So implement the counter. I give it any name I want. I'm just going to call it the counter impl of the I counter. So now I pass the actual value of the generic, which is the contract state. Now I have to implement. But as before, I have to tell this is not any regular implementation. This is actually the ABI of my smart contract. Again, an attribute. Now I have to implement, right? So I have to start with a get counter. And the get counter, we know that just decrease font size a little bit to be able to see the code on top, right? So first argument self, expect a snapshot of the contract state, right? The generic, but now it's an actual type. U32. And what it does is just basically you're just going to read from state and return that value. And to read from state, you do the same trick, self.counter, but now use read instead of write. And similar to Rust, if you don't put the semicolon at the end, it means that it's going to return the value. So that's all we need to do. Now we go to the increase counter. And we can actually copy this here. It's the same. Ref, it's the contract state. So now we have to first read what is the current value of the counter and then increase +1. So let's do here, let's say current counter equals to self.counter.read. And then we write the same value but +1. Say current +1. And we pretty much copy the same logic for decrease and just, put a minus here and decrease. Decrease, right? So now it's all green. It's all good. Our build. And it's passing. Let me see how we're doing in time. I have only 5 minutes left. So I don't have time to deploy it, but if you want to, if you're curious how to do it, basically you will need to have a CLI. And the one that I normally use is called Starknet. So you can use Starknet to deploy to either to testnet, to mainnet, and it has a handy documentation to tell you how to actually, because you will need to create a wallet to fund it with some tokens. In this case, you use ETH at some point to pay for gas fees. Eventually will be the Stark token. So in the 5 minutes that I have left, first of all, any questions you have about the code that I just showed you?
What actually differs in this language than Rust?
What is what? Sorry, could you repeat the question?
Like, what is it that's different than Rust in this language?
Oh, well, first of all, it's a completely different compiler, right?
Yeah.
Because it compiles to the Cairo VM. Well, actually, it compiles to Sierra, which is like an intermediate representative language, like an AST of sorts. And then it compiles to the Cairo VM. With Rust, you compile directly to the machine, bytecode machine, right? But then you have some differences in syntax, right? Like these attributes are different. The way you use interfaces or implement, I think it's different, but I think in their latest Rust, this was also used, if I'm not mistaken. I'm not sure, not following that closely, but it's very similar. Even you see Scar.toml is very similar to what you use in Rust as well. But the way that it works under the hood, completely different. It's just the syntax that looks similar. Make sense? Okay. Going back to my slides. So some of the next steps, if you're curious, want to learn a little bit more, if this loads, right? So the Cairo book is a fantastic resource to learn more about the Cairo, the syntax, how it works. To learn more about Starknet, there's a book for that as well. And we have 3 different workshops. We have the counter workshop, which is the one that is following today, but the most basic, because in the counter workshop, you will learn how to use events and how to deploy as well. Then you have the ownable workshop, which is going to show you how to actually reuse code using components, because I mentioned we don't have inheritance, but we have traits. With components, you can actually build reusable blocks that you now different smart contracts can consume. And it's cool because you can also use Open Zeppelin as well to consume those codes, so you don't have to do it yourself. We have a workshop for account abstraction, where you create your own custom wallet. We have Starklinks, which is an interactive tutorial to learn Cairo. Node Guardians, which is a very nice website to also have some quests to learn Starknet and Cairo. And then you have the Starks 101, which is a series of videos teaching you how ZK Starks actually work under the hood. But maybe even better, we have a Basecamp. There's a free 4-week bootcamp taught live. It's actually going to start this Thursday. And I'm actually the teacher, so I'm going to cover way more than I just covered today, because I will have much more time. So I'm going to go through the architecture, how data availability works, proof recursion, components, and do way more live coding as well. So you can register here for free for that course. And that's it for me.
Cool. Thanks very much, Dave. Not sure if there's any other questions. We just have 1 minute left. I don't know if you have Telegram info you want to leave for people if anyone wants to reach you after the fact.
Yeah, you can find me Telegram or Twitter using the same handle, Barreto David. So yeah,
Awesome.
but yeah, and you have the
Yeah.
sites as well. So
Awesome. Well, thanks very much. Yeah, this was the first of hopefully many of these kind of lunch and learn sessions for the team. Our next one is with Risk Zero. Kim Karstens from there on Feb 13th. And again, thanks very much for David for taking the time, and have a good rest of your day, everyone.
thank you for having me. Take care, guys. Bye.
Thank you very much.
Bye.